Hi there, and welcome to Chapter 2.5 from Stevens' Matrices, Vectors, and 3D Math. And we're going to break this up into two videos. So this is the first video. Alright, and it is, again, from Chapter 2.5, Lines in 2D and 3D. In this first video, we're just going to talk about lines in 3D, and then that generalizes quite naturally to 2D. What you might recall from 2D is a line that looked like this: y equals mx plus b. When we go to 3D, that doesn't work at all, and so we build a method. We have a method for creating lines in 3D, and then actually bring that back to 2D. So when you get to 2D, you'll actually now have two different ways to define a line: this way and the way that we're going to learn right now. All right, so we're going to do lines in 3D. I'm going to put this in full screen mode so that we get a little bit bigger picture here. Alright, so when it comes to doing a line in 3D, what we need is a point and a direction vector. Right, so if this is my 3D axis here, and suppose I have a point here and a direction vector here, then the line I want to create is the line that goes through this point and is parallel to that direction vector. Right? And the way I do that is I say, alright, well, if this is my point, x1, y1, z1, and this is my direction vector, which I call v, a, b, and c, then I actually have three functions or three equations that describe my line. They're parametric equations, one for each variable: the x form, the y, and the z. And the way they're set up is that the x value from the point is right there, and then the direction vector, this is actually called a direction number. The elements of the direction vector are called direction numbers, and so that goes here. Right? So it's x1 plus at, and then for y it's y1 plus bt, and then z1 plus ct. So you just combine the x and y parts of the point with the x and y parts of the direction vector, and you create your three different parametric curves. They're actually parametric lines, really. And so what we're going to do, it actually only creates one line. That sounded a little strange, like as if I was making numerous lines, but I'm not. When all is said and done, this is one line created by these three functions. And in order to get the entire line, I let t range from negative infinity to infinity. In other words, it's an infinite, it's an object of infinite length. Okay, and v is called the direction vector. The elements of v are called the direction numbers. And here's a little mini proof. We'll go through it fairly quickly. Suppose I have this point Q and it's on the line, right? And then what I know for sure is that PQ has to be parallel to v. Right, so when I write PQ, I'm just going to take Q and I'm going to subtract off P. So let me erase some of this so you can see the players here. So here's P, here's Q. To get PQ, I take Q and subtract P, right? So that's going to be x minus x1, comma, y minus y1, and you get this. Right? And we know that's got to be parallel to my direction vector. So what that means is x minus x1 has to equal a times some constant, right? And y minus y1 has to equal b times the same constant. Z minus z1 has to equal c times, again, that same constant. That way those vectors, one vector is a constant multiple of the other, right? And so this is just that first statement that I just said. X minus x1 is at. Y minus y1 is b times the same constant. Z minus z1 is c times the same constant, and I call it t. And then if you just swing your x1, y1, z1 over to the right-hand side of the equation, on all three of those, you get the parametric equations previously defined right up here. All right, so that's the mini proof. And if you're given a point and a direction vector, finding the parametric equations is really easy, right? So for the x portion, it's just the x value plus this times t. So it's 3 minus 2t. For the y portion, it's the y component of the point plus the y component of the direction vector times t. That's 0, so there's actually no t in this part. And then you take the 0 component of the point, which is 0, or the z component, sorry, not the 0. The z component of the point and the z component of the direction vector, and so you have 0 minus 1 times t, or z equals negative t. So once you get the point and the direction vector, you have all the parts to create your parametric equations for the line. Okay, and so what you learn in elementary school or middle school is that any 2 points define a line. So let's suppose we actually have just 2 points in the 3 space. What is the line that those 2 points define? Well, as we know from up here, we need a point, all right, and we need a direction vector. But unfortunately, in this problem, I'm just given 2 points, right? But the direction vector is easy, because if both of these points are on the line, the direction vector has to be parallel to that, right? Okay, so I let that be my direction vector. The line, the vector from P to Q. So that'll be my direction vector. So I'll take 1 minus negative 2, 3 minus 1, 5 minus 0, and my direction vector is right there. That's V, right? And then I get to choose either one of these points. I'll choose P, so my point is here. So I have a direction vector and a point, so I get negative 2 plus 3t, right there, 1 plus 2t, and then 0 plus 5t. Right. And so that's one form of this collection of parametric equations for this line. There's actually infinitely many. For example, I could have used QP instead of PQ. Right? I could have switched those around. That would have changed my direction vector by a negative sign. Right? This direction vector here would then just have negatives in there. I also could have used Q instead of P, or I could have used any point that you eventually find on that line. Right? So unlike a line in 2D where you have y equals mx plus b, where every line has a unique m and b, that's not the case with the parametric equations for a line. Right? There is not a unique form for the line, or a unique identifier. Right? Okay, so moving on, we talk about parallel lines in 2D. We're going to talk about parallel lines in 3D. Two lines are parallel if their direction vectors are parallel. Right? That should make sense, because if I'm over here and I have this one line, it has a direction vector like that. For it to be parallel to another line, their two direction vectors have to be parallel. Right? And so that's easy enough to show whenever you try to test for parallel lines, as is demonstrated in this example. I have one line, L1, another line, L2. Let's see if they are parallel or not. Well, you look for the direction vector for L1. The direction vector for L1, that's just negative 4, 0, there's nothing in front of it, there's no t, and negative 1. So negative 4, 0, negative 1. The direction vector for the second line is just 2, 2, negative 1, right there. Right? And so if you look at these two vectors, you can see pretty quickly that one is not a scalar multiple of the other, right? That's what we mean by parallel vectors. One has to be a scalar multiple of the other. But look, if you go from negative 4 to 2, that means you'd have to be multiplying each term by, what, negative 1/2. But if you take 0 times negative 1/2, you don't get 2. So, not parallel, right? On the other hand, if we take a look at this second example, line 1, line 2, the direction vector for line 1 is 0, because there's nothing in there, 1, negative 2. Alright, so that's the first direction vector. The second direction vector for line 2 here is going to be a 0, a 3, and a negative 6. A 0, 3, negative 6. 0, 1, negative 2. If you look at these two vectors, one is in fact a scalar multiple of the other. In fact, you get L2 by just multiplying, let's see, 3 times line 1. Actually, you don't get line 2. It's the direction vector for line 2 is 3 times the direction vector for line 1. So the direction vectors are parallel. And because the direction vectors are parallel, the two lines are parallel. Okay, so now the intersection of lines in 3D is much trickier than it is in 2D. In 2D, right, they're either parallel or they intersect, right? The thing about 3D is that you can easily have two lines that are not parallel, but if they're on different planes, you think of some sort of lateral distance between these two, then they don't have to be parallel and they still don't hit. And in fact, if you play a little game with your finger and do two lines in 3 space, it's sort of odd for them to even hit. You have to get pretty lucky. You have to be sort of aiming for one, right? So here's the process for determining if and where two lines intersect. Right, so suppose I have these two lines. I'm going to show you this through demonstration. Right. I have two lines. I want to determine if they intersect and if they do, where. Right. So here's the thing. If this here's the parametric equations for the first line. This is the parametric equations for the second line. If they are to intersect, then the x values must be the same. At the same time that the y values are the same and the z values are the same, right? So specifically for x, I'm going to need to set 2 plus t equal to 5 minus s, and that's what I'm doing right there. And then for y, I'm going to have to set 3 equal to 3 plus 2s, and that's what's going on right there. And then for z, I'm going to have to set 1 plus 4t is equal to 9 plus 2s. And by the way, I use t and s. They're different parameters. I don't want to use the same parameter for each line because they are distinct lines, and so I don't want to use t for both of those, because then you'd be solving, all you'd have are t's. You need to figure out the value of t and the value of s when these things hit. Okay, so what I have here is 3 equations, right? And I actually have 2 unknowns, t and s. So I want to set that into, I want to set it up in such a way that I'll be able to do this with matrices, right? So what I'm going to do is I'm going to get the variables on the left and then the constants on the right. So for this first equation, for example, I'm just going to take this negative s and I'm going to add s to both sides. I'm going to take this 2 and I'm going to add negative 2 to both sides. Then I'll have t plus s equals 3. And then for the second equation, I'll take 2s, I'll subtract 2s from both sides, and I'll subtract 3 from both sides, and that'll give me this equation. And then here, I'll subtract 2s from both sides, and I'll subtract 1 from both sides, and I get this equation. Right? So I have 3 equations that I can set up in matrix form now. So this first equation is just 1 times t plus 1 times s. Right, so that's the first row. The second equation is 0 times t plus negative 2 times s. And the third equation is 4t minus 2s. And the right-hand side is just 308. So if you think about this, casting it back into the form of chapter 1, that's ax equals b, and I'm trying to solve for x here, right? And you have to be careful because this is not a square system. So if you use Matlab and just say, alright, well, x equals a backslash b, or a inverse times b, it may well give you an answer, especially if you use x equals a backslash. If you do this backslash, it will find an answer, and it's a least squares answer, which means it might be the best non-answer, right? So you have to be careful. You need to go back and check to make sure it's actually an answer, or better yet, even do it by hand. Doing it by hand isn't that hard because it's just two variables, right? So if we proceed by hand, right, we're not going to do that in Matlab. I'll write this system in augmented matrix form down here. All right, this is the coefficient matrix, and that's the right-hand side. Straight up Gaussian reduction, Gaussian elimination. I'll take this first row, multiply by -4, and add it to the third row. I'll make that a 0. We'll make this a -6. Let's see, -12 plus 8. We'll make that a -4. And that's what happens right here. Right. Now for the second row, I would like that to be a 1, so I just multiply by -1/2. Makes that a 1, keeps that a 0. So that gets me here. And then I want to get rid of that 6 down here. So I'm going to multiply the second row by 6 and add it to the third row. It'll make that go away, but that will still be a -4. So this is your final matrix, and it's the augmented matrix in row echelon form. And what you should notice is this last equation says that 0 times t plus 0 times s equals -4. That can't be, right? You can't take 0 times s and add it to 0 times t and get -4. So there is no s and t for which these two lines are at the same place. In other words, they don't intersect, right? But it's also worth noting that they're not parallel, right? And that's the difference between 2D and 3D. Because if you look at the direction vector for this first line over here, that direction vector is 1, 0, 4, and the direction vector for this second line is -1, 2, 2. So they're not parallel, but yet they don't intersect. That's basically because they're just in different planes in 3 space. If you get lucky, or you line it up, or you intend for them to intersect, you'll find out that you do have an answer. And that's demonstrated in this example here. The first line is defined by L1, second by L2. Set the x's equal, set the y's equal, and then set the z's equal. Right? And then I want to get the s's to go over to the left, the constants to go over to the right. I have it in this form so that I have variables and their coefficients, constants on the right hand side. So I can write that as a nice matrix equation: 1, 1, 0, -2, 4, 4, -2. Right? So there's my coefficient matrix, my unknowns, and my right hand side. I put that in augmented matrix form. And again, I'm just going to try to solve it using Gaussian elimination. So I multiply by -4 again and add. I'll make that a 0, -6, and 0, right? So that's what happens here. And I'll go through the same procedure. Multiply by -1/2. Change my -2 into a 1. Then I'll multiply by 6 and add. Then I'll make that a 0, keep that a 0. And I'm left with this system. What's nice about this is that it looks like there's infinitely many solutions, but because there's only 2 unknowns, I just take this equation and cross it out. It means nothing, right? That just basically says 0t plus 0s equals 0. That's a meaningless row. But this second row, on the other hand, this one here tells me that s equals 0. And then this first equation says t plus s equals 2, but s equals 0, so t equals 2. If s equals 0, t equals 2. And what that means is that if I go all the way up to here, and I go back and I set s equal to 0 or t equal to 2, notice what happens. We'll go to this one. We'll do line 2 first. When I plug in s equals 0, I get 4, 3, 9. Now when I plug in t equals 2 to the first line, I get 4, 3, 9. So the point of intersection is 4, 3, 9, found by plugging either of those into the original lines, right? Okay, so that does have a point of intersection, and then this example also asks, what's the angle of intersection? Well, the angle of intersection, if I have two lines, all right, that's the direction vector for V1 for the first line, and suppose this is the second line, and V2 is the direction vector for that. The angle between the two lines is just the angle between the two direction vectors. So in order to get this angle, I have to get the two direction vectors. And again, that's easy to do. You just look at the coefficients of t in each one of these, right? So the direction vector for the first line is 1, 0, 4. The direction vector for the second line is negative 1, 2, 2. All right. So that's where I got these direction vectors down here. Right. And so to get the angle between, I use the cosine form of the dot product and divide by the magnitudes, or this is actually a formula floating around a couple chapters ago. Where I take u dot v over the size u size v. So when I take u dot v, I have 1 times negative 1 plus 0 times 2 plus 4 times 2. That gives me 7. Alright, and then the size of u is just the square root of 1 plus 0 plus 16. And the size of v is the square root of 1 plus 4 plus 4. That's the square root of 9. Do a little simplifying. I get the cosine of the angle. If I actually want the angle, I have to use the arc cosine, or the acos in Matlab. It generally spits out radians unless you have your calculator and you set it for degrees. So once you get your radians, you multiply by what, 180 over pi, and that'll give you your degrees. So the angle between those two lines, found by getting the angle between the two direction vectors, is just 55.5 degrees. But notice, in order to get the two lines, you really need to make sure they do in fact intersect. Okay. So, moving on, I want to take a quick diversion here to the distance between a point and a line. Right? And you'll notice, so this is the distance between a point and a line. It gives you this formula. But think of it this way. So here's a line, and then Q is the point not on the line. And the distance I want to find is really the shortest distance from Q to that line. In other words, that has to be a right angle. Right? So I have this formula up here, but I'll derive that formula from this little picture we have going on down here. So if you look at this distance is basically the sine of this angle here times the length of this side. So it's the length of PQ times the sine of the angle between them. But it's worth pointing out that this point P is any point on the line. You know, you could have put it here, or even over here. So P needs to be on the line. So you'll notice in your formula you have a P in there. That's just any point on the line. Q is the point you're worried about. You want to find the distance from Q to the line. And V is just the direction vector for the line. Right? And if we use trig, and we know that angle, we can get the distance from Q to P by the magnitude of PQ times the sine of the angle. But more than likely, we're not going to know that angle. Right? And that's what leads us to this formula up here. So what we do, we know that we want the size of PQ times the sine of theta. And if you go back to the chapter on the cross product, last chapter, 2.4, the cross product can be defined in terms of the sine of the angle between the two vectors times the magnitude of each vector. Right? And so what I'm going to do is I have an equation here. I'm going to divide both of these by the size of v. And what you'll notice is you're just left with pq times the sine of theta. In other words, you're left with this right here. Right, so this, or I guess I have it written right here, the size of PQ cross V over the size of V is the actual distance you're looking for. So if you have the angle, this is actually easy to do, but you probably won't. So this way we can do some trig without any trig. Again, the beauty of the cross product and the dot product is that you're able to do some trig without using any trig functions. So let's do a little example here. Suppose I have a point Q, and I want to find the distance from Q to this line. Well, in order to do that, I need to get P, which is a point on the line, and I need to get V, which is the direction vector. So P is easy to get. I just come back down to here, and I set T equal to any number I want. If I set T equal to 0, then I'll get 3, negative 2, 5. It'll be 3, negative 2, 5. And then my direction vector is just the coefficients of t. So it's negative 1, positive 1, negative 3. So negative 1, positive 1, negative 3. And actually I have them right down here. There's V, there's P, right? And so one of the things I need for my formula, which I'll rewrite it right here, so that distance is PQ cross V magnitude over the magnitude of V. Right? So I need to get PQ. That's easy enough. There's Q. There's P. PQ is just negative 1 minus 3. 0 minus negative 2. 3 minus 5. And it gives me the vector PQ. So if I want that cross product, I'll use the determinant of the 3 by 3 method that we used back in chapter 1. So it's just I times the determinant of that matrix minus J times the determinant of that matrix plus K times the determinant of that matrix. And when you go through all those calculations, there's that cross product. But I'm really only looking for the magnitude of this cross product right there over the magnitude of V. So the magnitude of the cross product is going to be, 16 plus 100 plus 4 be the square root of that, so square root of 120. And then the magnitude of V, V is right here, so I'm going to take 1 plus 1 plus 9, get the square root, so you get square root of 11. So the distance between that point, Q over here, and this line defined by these parametric equations is 3.303. And again, what that means is if I have a point and a line, that distance is the distance, the shortest distance to the line. Right? 3.303. Q, and this is the line. Alright, so that's a little divergence into the distance from a point to a line. I'm going to show you a little bit of Matlab stuff for plotting lines in 3D. And it starts with this function. Both of these, the function file here and then the program that uses it, are both in the Chapter 2 repository. I recommend that you open both of them up. The function file is plotline 3D. The program is plotting lines. So we'll take a look at this function file first. It basically plots a line in 3D. And you just send in the direction vector, a point that the line goes through, some t bounds. And what that means is when you do that, when we did the parametric equations for a line, we said, oh, t is between negative infinity and infinity. That gives me the full line, but that's infinite. So I'm really not going to plot the line from negative infinity to infinity. So it'll just be the lower bound here and an upper bound here. So that's what I'm looking for, t bounds. All right. It's actually a vector containing lower bound and upper bound. And then what color you want. And all this function does is it creates the parameter t that goes from the lower bound to the upper bound with 100 points. So you're going to plot 100 points to create this line. The x values will consist of the first part of the point plus the first part of the direction vector times t, second part of the point, second part of the direction vector times t. So what you're getting are actually three vectors, x, y, and z, all functions of t. That's why they're called parametric equations. The t is the parameter, and you create a vector for x, y, and z. And then you plot it using the plot3 command and send in the color. That is the last argument you put in here. So in this case, we plot three lines. The first line has this direction vector through that point. The second line has this direction vector through that point. Third line is this direction vector through that point. Right? And we do the first one red, green, and blue. Right? So the first one is here. Let's see where that. We'll just do that first line. The first line goes through the point 0, 0, 0. That's the red one, right? So that's 0, 0, and it's 0 height. So that's my point. My direction vector is 1, 2, 3. So it's basically 1, 2, 3. So that seems about right. And my t bounds go from 0 to 10. Right. So when you go from 0 to 10, you start here, you cruise along here, and you end up right there. Right, and then we do that with a green line and a blue line as well. So I recommend that you grab those out of the repository, run them, and well, you really can only run this one, and it calls that function file right here. Right. And then you can rotate it around, take a look at what these lines look like in 3D. So coming up next are lines in 2D, and we're gonna describe them the same way, parametric equations for lines. So we're not going back to y equals mx plus b. Those days are sort of behind us. So we're going to do the parametric equations for lines in 2D. It's just a natural reduction from the 3D case. It's actually really easy to do. The video is much shorter. With that being said, though, I do think it's best that we wrap this one up, and I will see you at the next video. All right. Bye.